everyone, I'm Yuki, and today I'm going to talk about the frequent sediment density flows during 2006 to 2015 triggered by competing seismic and weather events, observations from subsea cable breaks of southern Taiwan. Okay, so I'm going to talk about the study area. In this figure, we can know that there is a Gaoping Canyon here and the Manila Trench here. And the black line is the submarine cables, and there are at least 17 submarine cables here serving as the critical communication links between Asia and the global network. And the frequent earthquakes and the typhoons cause the multiple instances of cable damage, significantly affecting telecommunications and financial transitions. And the picture here is the submarine cables sketch map. And to talk about the research objective, we want to trigger in the mechanism of the sediment density flows, including the earthquakes and typhoons and the river sediment discharge. And also we want to evaluate the movement patterns of sediment density flows, such as the speeds and the pathway and the impact range. And we want to know the causes of submarine cables damage and the proposed protective strategies for future infrastructure. And to talk about the research methods, first we use the submarine cable data from ICPC to determine the time and location of cable breaks by using the TDR method to measure the signals, losses, distances, and accurate locate breakpoints, and calculating the sediment density flow speeds to comparing the time and distance between the ejections cable breaks to estimate the velocity of the sediment flows. And second, we compare the earthquake and meteorological data from 中央气象局 and the USGS and the NASA Typhoon database. And by doing this, we can analyze the earthquake magnitude and the epicenter locations. And also, we can assess in the ground shaking effects to evaluate the likelihood of triggering submarine landslides or sediment liquefaction, and to examine the typhoon-related rainfall and river sediment discharge to determine whether there exists the hyperconal threshold for Gaoping Canyon outflow, and I will elaborate this vocabulary later. Okay, and we use the GIS spectral analysis and terrain modeling. From the data is from IONTU and GeoBackhaul. And we're constructing a 3-dimension terrain model like this, we just mentioned. And by having the figure like this, we can know the sediment flow speed and seabed topography, and stimulate how sediment move along canyons and trenches. And so now we're going to talk about the results. There are 4 events we are going to discuss. And the first event is the Pingdong earthquake happened in 2006. And in this figure, we can demonstrate that there are 2 magnitude 7.0 earthquakes triggered at least 22 cable breaks. The blue square here means the cable breaks happened, and the orange circle and the red sears means the sediment density flows happen. In this figure, we can know there are at least 3 separate density flows were formed with speed reaching 5.5 to 12.7 meters per second. Is here and here. And its impact range is over 460 kilometers. The x-axis is the impact range. And the causes is because the instantaneous sediment liquefaction and slow failures due to a strong ground shaking. And the second event is the Typhoon Morocco happened in 2009. And when the typhoon hits, the Gaoping River experienced its largest record flood discharge, generating 2 sediment density flows. As we can see, there are 2 sediment density flows happen. And also, this event demonstrates that the sediment density flows can be delayed by several days after the rainfall. Like, there are 3 breaking times. So we can say they are leading to prolonged impacts. And the third event is the Jiaxian earthquake, happened in 2010. And in this event, the sediment density flow occurs 8 hours after the earthquakes, with a slower speeds around 5.9 to 7.9 meters per second. And we think the possible causes is the progressive small-scale slope failure accumulated post-earthquakes, eventually forming a large-scale sediment density flow. As you can see, the cable only breaks in a deeper area. And the last event is the Typhoon Sudler, happened in 2015. And in this time, the Gaoping River reached the hydrochronic threshold, but cable damage was limited to deeper cables. And so I'm going to talk about this vocabulary. And in this chart, we can know that the x-axis is the discharge of the river. And whenever it reaches the 4,000, we can know as the river water density is heavier than the sea water density. And the y-axis is the suspended sediments. And so we put the 4,000 river discharge here in y-axis instead and draw a line to say it's reached the hydrochronic threshold. And the x-axis is when the time that the typhoon hits. And so in this period, we can understand that the river reached the hydrochronic threshold. And after that, the cable starting to break. And so to look at these charts, we can know that the possible explanation is the sediments settled in shallow regions, preventing the formation of a strong sediment density flow in upper canyon sections. And to put 4 events together, and we can discuss the correlation between the flow speed and factors such as the runoff distance, seabed slope, and channel width is really weak. Okay, so here comes to the conclusion. First, both earthquakes and typhoons can trigger sediment density flows with impact ranges extending hundreds of kilometers. And second, the speed and range of sediment density flows are influenced by seabed topography. And third, the typhoon-included sediment flows may last for days or even weeks, making their impacts more complex than earthquake-included flows. And to talk about the future research, we can establish a long-term submarine monitoring systems to track sediment density flows in real time, and also develop high-resolution sediment flows predictions models to migrate risk to submarine infrastructure. And the last is the investigate similar phenomena in other regions to further validate sediment density flow characteristic under different environment conditions. Okay, and this is my presentation. Thank you.
What is the time domain reflectometry?
If we want to calculate the speed, we have to get the distance and the time, right?
Yeah.
And so when we want to know the flow's speed, so we have to get the distance of the time and the time when the cable breaks. We have a record, and it's really long, right?
Yeah.
So whenever it breaks here, and later on it breaks on the second place, so we can get the distance of the floor. And also we can have the time. And by have the time and the distance, we can calculate the speed. And this is what the TDR is.
So TDR is a method to measure the speed of
The flow.
the flow.
Yeah.
Okay, thank you.
Can I ask why there are question marks in the orange circle? What is that mean?
And we can demonstrate with this figure because there are also a question mark here in P3. And I just look in the article and it says they cannot sure if this is really happens because the signal is really weak, but they predict it's really happen. So let's put a question mark here.
Oh, okay, thank you.
Do you think it is possible to deal with the data source by MATLAB?
This is a good question. Actually, I think it's possible, but we have to.
It's hard.
Yeah, we have to learn more about it, so that we can deal the data with the different model.
Thank you.
Thank you.
I just wondering what this picture really mean, but because I didn't really get it. Can you describe this?
Okay. I can explain again. And like in the upper picture is the first events I just mentioned. It's in 2006 and it's in Pingdong and it's an earthquake. And I just take it from the paper and it's with Morocco. So we just look at this. In the x-axis is the impact range. Is under the ocean. Like this is the depth, and this is the kilometers along Gulf Canyon and Mariana Trench, and there are around 460 meters, kilometers, and the dots here, like we have a triangle and a circle, and with different colors means the different break time. So
The break is a cable break.
yes,
The point.
yeah.
Oh, okay. The red word here, the density is say the river water is. I just wondering why the river water's density is much than the seawater here.
Because the y-axis is the suspended sediments, like the particle in the water.
So there's a particle in the water, so the density is much
Yes.
than the seawater. Oh, got it. Okay.
Genius.
I think this talk, because it's probably relatively not so familiar to you because it's a geology topic. So I think as a speaker needs to prepare more information for the audience in order for them to understand what is the key point or importance of this study. In terms of the background, I think what was missing in the background, because the topic was about density flow triggered by some events, right? Did you have a slide where you explain density flows? First of all, you did not explain what is density flow. It's like you expect everyone to know what is density flow, but this is not the case. So please explain what is density flow. And maybe during the explanation of density flow, you can, at some point, also introduce the concept of hyperpycnal. You explain at the later stage using the data from the paper. But in fact, there are some cartoons on the internet that allows you to better explain the concept. What is hyperpycnal flow? So please also use cartoon and also use cartoon to explain density flow. And after you explain all this concept, I think the missing link here is you have to tell the audience density flow is the most difficult flow to monitor in the ocean. It is and it is also the fastest flow in the ocean. It is because it's very catastrophic, its speed was very fast. Therefore, there's no simple way to monitor it. That's the reason they want to use cable break. Okay, then everything is connected because you just go directly into Manila Trench, blah, blah, blah. But the general importance of the study was not mentioned. Okay. And then regarding the format of this, please add page number next time. Did you add it? Okay, so I can't really know where I should make notes. If you really want to put this map in your introduction next time, make it larger. This space is unnecessary. So make it larger. The font can be larger as well because you don't really need a space here. You need larger font, always larger font. And next time, please, because you are very familiar with your line, so you can look at them and speak louder. As I mentioned, if you speak lightly, it seems like you are not confident. So it's very important. Regarding these material and methods, to me, it's all technical. Actually, you can condense it, in my opinion. You can condense it. Here you have 4 events that you want to introduce. My recommendation is you can tell the audience you have 4 events. However, you only explain one event carefully, very carefully. For example, the Pingdong event is a very famous event. You can probably tell us before you go into, because when you were at this slide, you were very quick. Like, okay, I'm going to talk about Pingdong events next. So this has no information. So instead of showing all these texts, you can first tell us, like, what is the magnitude? Okay, what is the magnitude of this event? And then maybe you can find some photo showing the damage caused by this earthquake. I mean, on land, like the collapse of some houses, etc. How many people dead, etc. So you bring some feeling to the audience. Okay, I'm talking about a catastrophe. Here, this is what happened in the ocean, right? Takes time to explain this carefully. Put this one next to here and make it really, really large. So in fact, I couldn't read this text standing there. So I'm an old woman, okay? So I really can't read this. I'm surprised Sheila can see a question mark here. So I'm totally surprised. So the quality of the figure also needs to be improved because I didn't aware that there's a question mark here. Please make your map larger, clearer, and put this and this together, like a cross-reference each other to say, oh, this is the feature, what is what in this map and also in this transect. And then based on this data, what can be calculated? Okay, just one example, and it takes time to explain it. And after you clearly explain all the first case, all the other can be shown only shortly. Okay, and without this text, it's not necessary. You just say that I have the same type of data, and then show it like a map. The second case with transect, and third case with transect, last case with transect, and the best thing is you can always show some photo of the disaster from the news. Okay. Later, you are going to talk about this. I think it's related to the typhoon, right? After this, I think what really takes time, what you should take time to explain is these 3 figures, because they summarize these 4 events together to determine which factor determine the speed of density flow, which is very important because the faster the flow is, the more catastrophic it will be. Right? So that's the reason the author wants to know what determines the speed. So you should enlarge for each of them deserve one slide and introduce them carefully. What is X? What is Y? What are the symbols? And what are the conclusion? What is the conclusion for each of them? So don't use so much time to explain each individual case, but use time to explain this. Then conclusion. And next time, this is unnecessary for a talk like this. You can stop here. Okay, good. Hope to see improvement next time.